All right, in this section, we're talking about applications with growth and decay. These are applications of your logarithm function that we've been talking about. You've seen this application before, but they kind of take it a little bit in a different direction in this section. Similar, but a little bit different. You'll notice in 4.6, this formula shows up. So I say they just spiced up our PERT formula. We've seen this formula in the earlier section. It looked like A equals PE to the RT. This is our exponential growth or decay formula. We used it for money, like you could put in a certain amount of money, times it by continuous compounding with E to the rate times time, and it equals how much something grows to. If R is a negative rate, you can do a half-life, and we saw some of those already in earlier videos. But what you see in 4.6, this is the way the formula is written. But I want you to see it's really just the same as this. It's a little more mathematical jargon, I would say. So P sub t, we know that is like f of x notation. F of x means this thing is a function. But instead of using, the default f and x, it's using the letter p to say it's a function of what you start with, the p value, the present value, and t is a function of time. T is the variable that we're using for time. So there's no x in this problem. Instead of using just the default f, it uses the variable. That makes more sense in this application. So that's the only difference. So they call it p sub t, p of t, instead of f of x. So that's just function notation, or y equals, even if you wanted to think of it as that. And instead of just saying p, like in the PERT formula, it calls it P sub 0. We've seen the sub 0 notation before. It's just a more mathematical jargon way of saying this is the initial starting point. When we say sub 0, we're saying here's how it started, the starting value, which is really what that meant too. So again, don't let that bother you. E is still E. And instead of calling it R for rate, we're using K in this section. So K is its constant rate of growth or decay. If K is a greater than 0, a positive number, it's growth, right? So a positive rate, but it's still just rate. They've just changed up our variables on us a little bit. So when you see that, if you're reading it in the book or you see it in your homework, just know that's a fancier way of saying the same thing we've been doing, okay, guys? So no biggie there. Just wanted to explain that. Okay, so moving on down, the first example we're going to look at using this formula is females in the Olympics. So read along with me here. It says in 1985, the number of female athletes participating in the Summer Olympic type games was 500. In 1996, there were 3,600. And that was in Atlanta, by the way. Assuming that it's an exponential growth model, can you plug it into this and figure out the rate of growth? Can you find K? So the first question is find the K value, given the information we have. And again, assuming it's an exponential growth, which means it fits that curve. That's our exponential growth curve, right? The basic curve like y equals an a to the x. Any base greater than 1 has this exponential growth curve. So assuming it's an exponential model, fits that model, find K. All right, so what did I say? I said the beginning amount in 1985, or the beginning that we're going to analyze from 1985 was 500. We don't know what K is, but from 1985 until 1996, we can do that calculation. That's 11 years. So you put in 11 for T, and it grew to, what did I say? 3,600 participated in 1996. 3,600 females were in the Olympics in Atlanta in 1996. So there we can plug in, and if you only have one unknown, we solve equations. That's what we do in algebra. So we can figure that out. First step, you all should be getting real used to this. We've done this so many times now. You divide by the p-value, right? That's first step. Then over here, I say divide it. If it's not, a bad decimal, we'll divide it all the way. Otherwise, we'll just reduce it a little bit. So let me check that out. 3,600 divided by 500 is a nice decimal. We don't have a lot of those. Comes out terminating decimal 7.2. And then e to the k times 11. So the next step, every time we do one of these, is we take the logarithm of each side. We always take the logarithm if we're trying to bring the exponent down. Solve for the exponent, unknown exponent, it means take the log. That has been our new thing in the last couple of sections, is logarithm rules, bring the exponent down as a multiplier. So K11, or let's call it 11K, turn it around, and no equal. When that's brought down, it's times ln of e. ln of e, we keep seeing that's just 1. So we got 11K equals this. Let's divide out the 11, and then that solves for K. Everybody press that in your calculator and check that out. All right, so we are getting a value. We solve that and get K equals 0.17946. So it's a positive number. Growth has occurred, which we knew growth had occurred because it went up. All right, so now that we know what K is, we can write our model. So we can rewrite this as the growth model, and I'm just going to call it PERT, you know, the old jargon we've used, and say p-value, we started with 500 female athletes. That was our original amount on this model. Now we've figured out what the rate is, 0.17946 t. So that would be the growth model. We have modeled, and we should be able to put in whatever year that we want here, year 2, year 3, year 25, and see how many female athletes we can expect if the growth continues as it has been. All right, so I have a question for you on this next one. It says, so predict, according to this formula, what about the year 2000, according to this model? And these are things we can Google. We could find out how many were in 2004 and so on, and see how close this model would be. So if you want to do that. But let's just do, according to the math we're doing for our example, what about the year 2000? Now remember, it starts at 1985, so whenever we do the year 2000, that's 15 years later. So we would do 500 e to the 0.17946, and we would put in our 15 years. And then type that in your calculator. And it says there should be 7,380 female athletes in the year 2000. Again, feel free to Google that and see how close it is. Okay, and another example, we could do any year, just according to this model, what does it think should happen? 2004, instead of 15 years later, that's 19 years. So that's 19 years. So we plug 19 in for t. So what we do in our calculator is A equals 500, the original P, e to the 0.17946, the rate we found, and then we plug in the 19 years. All right, again, check that out on your calculator, and I'm getting 15,129. So, do you think that's right? I don't know. You have to look that up. But is that, can we put in the year 2050 and expect it to be correct? Or do we eventually get to a place where it's kind of ridiculous and we've saturated the market kind of to say that it's leveled out maybe? So that's something about exponential growth. A lot of the models in real life, you have this quick growth where something is catching up on that little growth curve. It's a quick growth, but at some point it levels out and it's up equal, and it doesn't just continue to grow forever like that. So possibly that's what you would see when you Google. You'll have to check that out. All right, next thought. Example 2, we want to talk about COVID. So anytime we talk about a growth model and exponential growth, you might remember COVID-19. We saw a lot of graphing during COVID-19, and we'd say that it's an exponential growth, that it started out slow and then all of a sudden, boom, it was multiplying and just growing quickly. That's what exponential growth looks like, is a quick growth. And then eventually it levels out. But the curve of it, that's exponential growth, looks like that. So the next example, I took some stats from, I live in Boyd County. Ashland Community and Technical College is located in Boyd County, so I used their stats. And so you could look this up. And the first confirmed case of COVID-19 in Boyd County was on March 31st, 2020. And there was 4 cases reported that day. So we're going to do 4 as our initial model here. And we're going to say another data point, like let's check anywhere you want to on that. You could look through different stats and pick any old day and try to figure out a model. We're not saying it would be perfect, but it would be a model to represent what's happening. So let's see, I picked a day. What day did I pick? I picked 201 days later, a sample point that was day 201. So if you see that on my sample here, and I found there was 589 cases that day. So the A value was 589 cases, sorry. And that was 201 days later. So we're trying to figure out K. What do we think the rate of growth is at day 201? So just like the last problem we did, we find our own K value. We can divide by 4 to reduce this. K times 201. Do that on your calculator. And what is that? I don't think I showed that. I think I just said here's what the answer is. But what you would do is divide 589 divided by 4. And you know I only write that down if it's a nice decimal. It is 147.25. And then I need to take the log of each side. So the log of this side. And then we take the log of this side. The reason we take the log is so the exponent comes down in front of that. So we have the log of 147.25 equals K201, or let's call it 201K. It looks better that way. Times ln of E. ln of E is 1, so that cancels out. Then to solve for K, we divide out the 201. And then that is what we put in our calculator to figure out an estimated K value for our growth in Boyd County. Okay, and this comes out to be 0.0248 and some decimals. So now we can rewrite our growth model. What we expect to model the data for us as the original case 4. And then now we've figured out K is 0.0248, however many decimals you want to show there, times T. So that would be our growth model. And then we can do all kinds of different days. So maybe day 250. If you put 250 in for the time, type that in your calculator, see if it's accurate. Because I've got the data from quite a few days there on your chart there. So you can check different amounts from that. All right, but that's modeling data, finding growth models. All right, example 3. We're going to move to a doubling time. Now, we've seen this before. It just comes back up again, though, in the same application. Doubling time, another question that's often asked is what is the doubling time for a model? So if an initial amount, let's say, is $500 or 500 people or 500 whatevers, how long does it take that to double? So again, we're using the PERT formula, the exponential growth formula. If we've got 500 of something and we want it to double over here, say to 1,000, and we need to know the rate is given, different rates that matter. Oh, we're doing my same COVID problem. So let's say if we were doing COVID, but I think I went back to the female athlete. So I've gone back to the female athlete example. The female athletes, we had a rate of growth for the female athletes, but we could do it with COVID or with anything. But we have this rate was what we found a little bit ago for the female athletes' rate of growth. So we put that into that model. How long do we think it takes the 500 original female athletes in 1985 to be 1,000 according to this model? That's a doubling time. We would divide by 500. 1,000 divided by 500 is 2. That cancels. And then we solve that by taking the ln of each side. We've done that quite a few times now. And it comes out to be T equals 3.86. So about 4 years. According to this model, it would take about 4 years for there to be double the number of female athletes in the Olympics. And then we could say, what about tripling? We could do a triple time. Now, you might remember there's a shortcut to this. Anytime you do doubling time, double time, it's always ln of 2 divided by the rate. So we had the rate here. We could put that right down there. The calculation is ln of 2 divided by that rate. That should confirm what we've got here, 3.86. But again, that's a double time. If we wanted to triple, it'd be ln of 3 divided by the rate, or any other increment of time that you'd like to do for that growth model. All right, so we'll come back, talk about other applications in the next video.